What you just heard is called the Doppler effect. And you heard this when a police or an ambulance is approaching you or moving away from you. So when an ambulance or police approach you, then the wavelengths in front of the source, which is the police or an ambulance, are compressed. So it makes shorter wavelengths or higher pitch. And in the back, it makes longer wavelengths or lower pitch. So in front, you see higher frequency, higher pitch. In the back, you see lower frequency, lower pitch. So to determine or calculate the new frequency, or the frequency that is actually heard, not the one that is produced by the source, so it's called frequency with a dash, the new frequency, you will take the velocity of the sound or in the medium where all this is happening. So you take the velocity of the sound that is produced, how fast the sound can travel, or any other like light or in that medium, but we're going to be talking about the sound. So if you take the velocity of the sound in this medium, and if your source is not moving, and if your object is not moving, object is the observer, so I'm going to say here is the observer and here is the source. So S for the source and O for the observer. So if the observer is not moving, you will have 0 instead of the observer. If the source is not moving, you will have 0 instead of the source. And then times the initial frequency, the frequency that is produced by that source. Let's look at this example to understand how to choose the positive and the negative signs in the denominator and the numerator. So if you have the source that produces the sound, and you have an observer that is listening to that sound, if the source is approaching to the observer, then you have higher frequency. Higher frequency means you are compressing the wavelengths in front. So to get the higher frequency, you take the velocity of the source. So here is the velocity of the source. And you need to make the new velocity higher because the frequency is going to be higher, the wavelengths is going to be shorter. So to make this number, the new frequency, higher compared to the old frequency, you have to subtract the velocity of the source. And because the object is not moving, you don't add, or you just add a 0 over there. So let's say it's a sound and it's in the air, and the velocity of the sound is 340. So this v would be 340, this v would be 340. But then velocity of the object is 0 because velocity object is not moving. And then for velocity of the source, you subtract, because when you subtract, you make the denominator smaller, then you make the new frequency larger. Let's say here is another example. I have a source and I have an object. An object is moving toward the source, and the source is moving away from an object. So there is the velocity of an object and there is the velocity of the source. So if the source is moving away from an object, then your frequency is lower, or this action makes the frequency, the new frequency, lower. But if an object is moving toward the source, that makes the new frequency higher, because object approaching the source will compress the wavelengths in front of the source. Source moving away from the object will stretch the wavelengths by the actions that the source does. So in this case, I have to, if the source is moving away, it makes the frequency lower. So to make the frequency lower, I have to add in the denominator. If the object is approaching the source, it makes the wavelengths shorter or compressed by its actions. So that means it makes the frequency higher. Then I have to put a positive sign in the numerator as well. Here's another example. I have the source approaching the object, and I have an object moving away from the source. So I have the velocity of the source and I have velocity of an object. So in this case, the source approaching the object make the higher pitch. To make the higher pitch, I need to subtract in the denominator. The object is moving away from the source. It causes lower pitch. To make the lower pitch by the action of the object, I have to subtract in the numerator. So let's look at some questions where we can apply this knowledge and figure out the velocities and the frequencies of the object heard when they are both moving or one of them is moving. So here is the first example that we will look at. A particular bat emits ultrasonic wave with frequencies 560 kilohertz. The bat is traveling at 20 meters per second toward the moth, which is flying away from the bat at 8 meters per second. The speed of the sound is 340. Assuming the moth could detect the waves, what frequencies waves would it observe? So we need to find the new frequencies. So I'm gonna say the new frequency is equal to the speed of sound in the medium plus minus the velocity of observer and the velocity of the source. And then I take the initial frequency. So the speed of sound in the air, they said 340. So I know this goes 340, and here I have 340. Then I have the velocity of observer, that's a moth, so that is 8 meters per second. And the velocity of the bat that emits the ultrasonic waves is 20 meters per second. The frequency that it emits is 56 kilohertz, so 56,000. So I will have to multiply by 56,000 hertz. Now I have to decide where to place my positive and negative. So the observer is the moth, and the moth is moving away from the bat. So for the observer, the moth is moving away, so that makes the frequency lower. So I'm gonna subtract, because moving away would make the frequency that the moth hears lower frequency. But the bat is approaching the moth. So because the bat is approaching the moth, it makes the new frequency higher. To make the new frequency higher, I also have to subtract in the denominator. So now if I calculate the frequency that the moth hears, I will have 58.1 kilohertz. The next part, they say, okay, now the waves reflect off the moth and detected by the bat. What frequency are the waves detected by the bat? So now the source becomes the moth because it emits the waves. So another frequency, the new one frequency, is equal to, again, the speed of sound is 340. So I'm gonna plug in 340. My observer is now bat and moving at 20 meters per second. And my the source in this case is the bat, so that is 8 meters per second. The frequency that the bat emits is 58,100. and I need to determine the signs in this case. So the source is moving away, so that makes lower frequency because it's longer wavelengths, so I will have to add for the source. And the observer is approaching, that means compressing the wavelengths or making higher pitch, so I have to add to make the higher frequency compared to the one that is emitted. And if I calculate this number, I will get 60.1 kilohertz. The same things that happen to the sound happen with the light. So the light is part of the electromagnetic radiation. So here is electromagnetic spectrum. And this spectrum has radio waves. They have the longest wavelength, so radio waves, microwaves, and then infrared, visible, ultraviolet, X-ray, and gamma rays. So you go from the longest wavelengths for the radio waves to the shortest wavelength for the gamma rays. And you go from the lowest, so longer waves, lower frequency, and the higher frequency with the shorter wavelengths. And the visible light falls somewhere in between. I once read somewhere that if you take a film, the film that they record the videos. So if you take a film and you stretch it all the way from Mexico to Canada, then the visible light is gonna fall somewhere in the middle of the United States, and the length of it will be only about 2 inches. So the visible light, the one that your eye can detect, is really small part of the electromagnetic spectrum. And because of certain proteins in the eye of the bird, they can see the magnetic field of the earth, so they can see different frequencies that we cannot see with our eye. But anyway, so you have visible light somewhere in between. So infrared on the longer wavelength, and ultraviolet on the shorter wavelength, and you have infrared, so it starts from red and it ends with the violet color in the visible light, and all the other colors in between. So red color has the longest wavelength, and blue or violet color has the shortest wavelength. So sometimes you hear the words like redshift. So our universe is expanding. So because of the expansion, we have all the stars moving away from each other, or galaxies, and they're redshifted. Redshifted means their wavelength is longer, appears to be longer than it should be. So because they're moving away very fast, they're redshifted. So their wavelength is stretched. We don't learn in AP Physics 1 a lot with the waves, with the light waves or the visible light or electromagnetic spectrum, but we do this in AP Physics 2. But there might be questions related to you understanding it conceptually. I haven't seen questions after they split into AP Physics 1 and 2 on Doppler effect, where you have to apply the formula. But I still want to cover it so you are familiar, and if you ever see anything like this, you will know how to solve questions using the formula. But you also need to understand that this Doppler effect applies not only to the sound waves, but also to the light waves as well. Here's another example. What is the frequency heard by a person driving 15 meters per second toward the blowing factory whistle that produces the frequency of 800 hertz if the speed of the sound is 340? So again, I'm gonna start with a new frequency that is heard, and you can also say its initial frequency times the velocity of sound in the medium, which is 340 that they give you, plus minus and plus minus, and then you have the velocity of the observer and the velocity of the source. So now we have the frequency that we have is 800, that is produced by the factory whistle. The velocity of the sound in these conditions is 340. The observer is moving, the source is not moving. So for the source, I don't have to write anything at the bottom in the denominator, but the observer is approaching. Because the observer is approaching, he is causing the frequency to increase or make the higher pitch, the wavelength, shorter. So I have to add with the velocity at which he is moving, which is 15. So the new frequency that is heard by the observer is equal to 835.3 hertz. Here's one more question. While standing near a railroad crossing, a person hears a distant train horn. According to the train's engineer, the frequency emitted by the horn is 440 hertz. The train is traveling at 20 meters per second toward the person, and the speed of sound is 346. What would be the wavelength of the train's horn if the train were at rest? So if the train was at rest, you have the velocity is equal to the wavelength times the frequency. So if you want to calculate the wavelength, you have the velocity 346 divided by the frequency that it produces, which is 440, and that will give you 0.79 meters. And for the second part, they ask you by how much is the horn's wavelength changes as a result of the train's motion. So the frequency changes. So I have the frequency, the new one, is equal to, and here I have initial frequency, which is 440 hertz, times the speed of sound in these conditions, 346, and the person is not moving, so the observer velocity is 0, so I don't have to worry about the observer velocity, but the source is traveling toward the person, toward the observer. So if the source is traveling toward the observer, he compresses the wavelengths or he increases the frequency. So that means I have to subtract here to increase the frequency. So I'm going to subtract velocity, which is 20 meters per second. And that will give me the new frequency of 467 hertz. So if I have the new frequency and the speed of sound is still 340, so the new wavelength is equal to still the same 346, the velocity of the sound, divided by 467, and that will give me 0.74 meters. So this is the new wavelength. Because the question is stating by how much the horn's wavelength changes, and you can see it changes by, so the change of the wavelength is equal to 0.05 meters. Here's one more example I want to look at with you today, and you're standing at x equals 0 meters listening to a sound that is emitted by frequency f sub 0. The graph above, or on the right, I moved it to the right, shows the frequency you hear during the 4 seconds interval. Which of the following describes the sound source? So is it moving to the left, from the left to the right, and passes you at 2 seconds? Is it moving from the right to the left and passes you at 2 seconds? Or is it moving toward you but doesn't reach you, but it does reverse its direction at 2 seconds? Or is it moving away from you until 2 seconds and then it reverses its direction and moves toward you but doesn't reach you? What I see from the graph is that the object is having lower pitch and then it has higher pitch. If it has lower pitch, then that means at first it's moving away from you, and then all of a sudden at 2 seconds it has higher pitch. That means it reverses direction and now it moves toward you. So from all the choices that I see, I think D is going to be the correct answer for this problem. Here's another question that we want to look at today. And sitting on the beach at Coney Island one afternoon, Sunny finds herself beneath the flight path of the airplanes leaving an airport. What frequency will Sunny hear as a jet whose engines emit sound at frequency 1200 Hz flies toward her at the speed of 200 meters per second? So we're given the frequency that it emits and the speed that it moves at. And again, I have to find what frequency, the new frequency. So again, I'm gonna say the new frequency is equal to the initial frequency and then the speed of the sound is not mentioned, so it's the speed of the sound plus minus the velocity of the object or observer. Observer is not moving, she is listening to the sound. The velocity of the sound again plus minus and the velocity of the source. So the frequency that is given is 1200. Then I have the velocity of the sound not given, so I'm gonna take 340 and 340. And the source is moving, Sunny is not moving, so I don't have to say plus or minus 0. But the source is coming toward her. If the source is coming toward her, the frequency is increasing. If the frequency is increasing, my denominator should be smaller. And here I have 200 meters per second. So the frequency that she hears is actually 2914 Hertz. For the second part, they say, what if the jet was moving away from her at the same speed? So if it was moving away from her, then she would have, again, initial frequency, which is 1200 of the jet, right? Frequency of the jet. Then 340. She's not moving, so again, it's plus minus 0. And then the bottom part is plus minus the velocity. If the jet is moving away from her, it stretches the wavelengths, makes higher or longer wavelengths, so or lower frequency. So I have to add 200, and that will give me 755 Hertz. I think I will stop here. The questions are pretty easy if you understand the movement of the source and the movement of the observer, and it's just one formula. And so you need to understand that the light waves also follow the Doppler effect, and the sound waves traveled also follow Doppler effect. So I'm gonna stop here, and this is our last video 6 on waves and oscillations. And if there are more videos related to sound and waves that you ask me to record for you with some problem explanation, then I will add the links in the description of this video. Otherwise, the next video you will have in our lessons is going to be on charges and circuits. And thank you for watching this one. I'll see you in the next one.